Hi everybody, I am Apeksha GUNDALE and today we are going to learn properties of gravitational force. There are three properties of gravitational force. The first property is that gravitational force is the weakest force in the universe, as the value of it is very small, that is 6.67 into 10 raised to minus 11 Newton meter square per kg square in SI unit, and in CGS unit its value is 6.67 into 10 raised to minus 9 centimeter square per gram square. So as its value is very small, therefore it is the weakest force. Then gravitational force is only the force of attraction. That is, that gravitational force never repels, it only attracts. And third property is force on the body 1 by body 2 is equal to the force on body 2 by body 1 according to Newton's third law, and this negative sign indicates that the direction is exactly opposite. Now, the Newton's law of gravitation. According to this, we get the equation that gravitational force is equal to capital G m1 m2 upon r square. Here, capital G is universal gravitation constant. m1 and m2 are the masses of body, and r is the distance between bodies, and F is gravitational force. So now, let's do a numerical based on this. So the numerical is, if the distance between the two masses is doubled, then what is the new gravitational force? So, as we know that gravitational force is inversely proportional to the distance square, so F1 upon F2 is equal to R2 upon R1 square, as it is inversely proportional. Now R2 is double, so we get that 2R upon R whole bracket square. So R get cancelled and we get 4 upon 1, and it is the answer of F1 upon F2. So therefore F2 is 1/4 of F1. The scientist Galileo Galilei is the first scientist who studied the motion of the different bodies under gravity. He do the experiment that he take the three bodies of different weights. One is of 1 kg, other 10 kg, and third is of 100 kg. And he just fall them on the surface of the earth, but height is same. And he observed that all the bodies require same time to reach on the earth's surface, and he called this as the free fall. So therefore, as it is the free fall, u is equal to 0, and when we put these values in the kinematical equation, second kinematical equation, as h is equal to ut plus half at square, here u is equal to 0 due to free fall, and a is equal to g as it is gravitational force. So we get that h is equal to half gt square, and in the value of t we get in root 2h upon g. So therefore time is same for all the bodies. At here there is no term of mass. Now we will derive the relation between small g and capital G, that is gravitational force and universal gravitational constant. So if it is planet and it is the body which is on the surface of the planet, so the radius must be r. We neglect the radius of body as it is dimensionally very small compared to the radius of planet. So we have the equation that force is equal to capital G capital M small m upon capital R square. Here capital R is the radius of planet, capital M is the mass of planet, and small m is the mass of body. As we know that force is equal to mass into acceleration, so we can put the value that force is equal to mg, and it's equal to g mm upon capital R square. So mass get cancelled and we get that small g is equal to capital G capital M upon capital R square, and hence we derive the relation. Let's do one numerical again. So the numerical is m1 upon m2 is half, and the radius of first planet is 4 times that of second planet. So we have to calculate the ratio of acceleration due to gravity. So we get that radius of first planet is 4 times that of second planet, and we have the relation that g small g is equal to capital G capital M upon capital R square. So we get that small g is directly proportional to capital M upon capital R square, as g is the constant. So g1 upon g2 is directly proportional to m1 upon m2 and inversely proportional to the radius. Therefore it will be r2 upon r1 into bracket square. So we here get that r1 is equal to 4r2. Therefore r2 upon r1 is equal to 1 upon 4. So we get g1 upon g2 is equal to m1 upon m2 is given in the question, that is half. So half into 1 upon 4 square. So we get this as 1 upon 2 into 1 upon 16, and it is equal to 1 upon 32. So the ratio of acceleration due to gravity is equal to 1 upon 32. We must express the acceleration due to gravity in terms of density of the planet and radius of the planet. So here let the capital M be the mass of planet, capital R be the radius of planet, rho is the density of planet, small g is acceleration due to gravity, and capital G is universal gravitational constant. Now we have the formula that small g is equal to capital G capital M upon capital R square, and as we know that mass is equal to density into volume, so mass is equal to rho into capital V. So we replace mass as rho into capital V. So we get that G capital G upon capital R square into rho into capital V. As the shape of the planet is sphere, so the volume of it is 4 by 3 pi r cube. So when we place this value, r cube and r square get cancelled. So we get the value that small g is equal to 4 by 3 pi capital G in bracket r into rho. So g is directly proportional to capital R and rho, that is radius of the planet and density of the planet. And at last we will see the difference between capital G and small g, that is gravitational constant and acceleration due to gravity. So the first difference is capital G is the universal gravitational constant and small g is acceleration due to gravity on any body. Then the second difference is numerical value of force of attraction acting between two bodies of unit masses separated by unit distance called as capital G, and the small g is acceleration produced in freely falling body due to the force of attraction on the earth. Then the third point is unit of capital G is Newton meter square per kg square and unit of small g is meter per second square. The fourth point is g is the universal constant and its value is 6.67 into 10 raised to minus 11 Newton meter square per kg square, and the average value of small g is 9.8 meter per second square. Capital G is a scalar quantity, while small g is a vector quantity. Then the value of capital G is same at each place, but the value of small g is different at different places. So, thank you.